Hello everyone. Today we're talking about inverse trigonometric functions, just a simple explanation of where they come from, why we care about them, and then an example problem. So in math, there's two different types of inverse functions, right? So it's a common misconception that if we have the inverse sine of x, that's just 1 over the sine of x. That's actually cosecant. We don't need to write it that way. And so if we're taking the whole entire sine of x over 1, that does become cosecant. But what we're looking at is the second definition of inverse in math, where you're switching the inputs and the outputs, the x and the y, kind of like what you were doing in college algebra. You switch the y, and you switch the x, and you solve for y, and you get the inverse function, right? So when we're taking the sine function, we're taking an angle and we get a ratio out, right? And the sine gives us the ratio of the opposite over the hypotenuse of those triangle legs. And then you also get the inverse sine. You want to have this ratio, and you're asking what angle creates this ratio. And so you're getting, you're taking the ratio of the opposite of the hypotenuse, and you get that angle that creates it, right? So with these inverse trig functions comes some range restrictions. Many of you guys have heard the phrase, all students take calculus. Hopefully you will. Then this phrase just tells us when sine, cosine, and tangent are positive. They're all positive in the first quadrant, sine's positive in the second quadrant, tangent's positive in the third quadrant, and cosine's positive in the fourth quadrant. And so if we kind of isolate these individual trig functions, we see that sine, in a sense, is reflexive over the y-axis, because sine is positive both in the first quadrant and the second quadrant, and then negative in the third and fourth quadrant. So we just isolate it to be only positive in one quadrant and negative in the other quadrant. We don't really care about those quadrants. So we get that the arc sine of x is, the range is from negative pi halves to pi halves. And similar thing for cosine, only it's reflexive over the x-axis. And so we restrict it to just be from 0 to pi. And the tangent also follows the same restrictions as sine, and it's from negative pi halves to pi halves. So we can also understand these domain restrictions in a different way if we just graph them, right? Because we know that a function needs to be one-to-one. So we take sine and we flip it over the y equals x-axis, and we get this cool looking graph that is definitely not a function. And so we restrict the domain to negative 1, 1, and then the range is also restricted because of that domain restriction. And so these are the subsequent resulting graphs that come from those domain restrictions. There's sine here, and cosine, and tangent. And now we have our example problem. We have the inverse cosine of 3 over 5, and we're taking the tangent of that. So how I like to start this problem is I break it down. I go from the inside and then out. So let's start with the inverse cosine of 3 over 5. Okay, so I'm thinking inverse sine, have a ratio, and you want an angle that creates that ratio. So inverse cosine, we have the ratio of the adjacent to the hypotenuse, and we're getting an angle out of that. And we're just going to call that angle theta. So we're going to draw that triangle, because the best way to solve a trig problem is always with the triangle. I mean, it's even in the name, right? Trigonometry triangle. So we can solve using the Pythagorean theorem for the opposite side, right? And we just know that's 4. We can either do like 5 squared equals 3 squared plus x squared and solve for x. But we know that's 4, and I don't think we need to go into detail on that. And we have our angle that creates that triangle. So we could, if we wanted to, put like the inverse cosine of 3 over 5 in a calculator and get some answer out. But there's an easier way to do this if you just say, okay, so we're taking the tangent of theta now, right? And we just, for tangent, we just need the ratio of the opposite over the adjacent. So that's simply going to be the tangent of theta is 4 thirds. So we know that the answer and the solution to this problem is actually just 4 thirds, which is kind of cool how you can just draw the triangle out and think about it, and then take the ratios that you've created to get the ratios that you've created from the one angle that you're taking the inverse of to get the next, the tangent of that. Here are some of the sources that were used in the making of this video. If you'd like to learn more, I'd recommend these, or just Googling inverse trigonometric functions. I hope you have a wonderful day, and good luck with trig. Bye!